this lecture, we will be considering material defects. As you well know, throughout this course, material defects play a very significant role in determining the strength of the material. In fact, many alloys can be designed with additions of very small percentage of a solute atom to give it a very large change in its mechanical response. And we'll see that the design process of materials relies on a deep understanding of defects. Although the course is not going to be based on physics of defects, but in this lecture and perhaps the next lecture, we will try to make a simple connection between the defects and their types of materials and the strength and the mechanical properties of materials. So what we will do in this lecture, as you see here, is that we will first introduce you back to crystal structures. I think many of you have studied material science courses and you know something about crystal structures, so we wanted just to remind you of the crystal structures, and then I will introduce the types of defects, point defects, line defects that we call dislocations, surface defects such as grain boundaries, and also volume defects like voids, for example. And then we will spend a little time on dislocations to show you the basic properties and how dislocations are related to the real strength of the material rather than the theoretical value of the shear strength. The last part of the lecture is going to cover just a discussion of the modes of plastic deformation. As you will see in the lecture, the plasticity is a process by which the material deforms in an irreversible fashion. Once you remove the loads, the mechanical loads, then the material doesn't go back to its original shape. And several mechanisms have been identified at the atomic scale that can lead to irreversibility of plastic deformation. So we will describe the process of slip, which is related to dislocations, the process of twinning in crystals, and grain boundary sliding and diffusional creep at high temperatures. So let's first spend a little time on crystal structures. Crystal structure is defined by space points, and each point indicates a position in space, and this position can be associated with a single atom or it can be associated with a molecule. The lattice described by this method is called a Bravais lattice. And for our purposes in the course, we will not look at complex Bravais lattices that you will see in geology, for example. We will confine ourselves to 3 different types of crystal structures, and they encompass a wide variety of metals that are used in practical design. So as you will see here, you have the face center cubic type of crystal structure, and in this crystal structure we have one type of atom on the corner, and since the corner is shared amongst 8 different cubes of similar cubes, then the share of one single cube of this particular atom is 1/8. Let me write it clearly. So we have 1/8. In addition to the corner atom, we have another atom also, but this atom is situated at the face between 2 different cubes. So the share of each single cube of this atom is only 1/2. Since we have 8 corner atoms, then we would have 8 times 1/8 that belong to one single cube. And then we have 6 faces, and each face contributes 1/2 atom. So the total number of atoms for an FCC cube is equal to 1 plus 3 is equal to 4. So we have 4 atoms that are dedicated for one single cube. Examples of this kind of crystal structure are copper, nickel, some steels, and also lead and aluminum. And then we have 2 other types of crystal structures that are also used in design. The next one is called body center cubic structure, BCC. And body center cubic structures, we have also 2 types of atoms, one at the corner and then one exactly in the center. So the number of atoms per cube in this case is 1 plus 1 equals 2, because we have 1 in the center and 1 on the edges. The last type of crystal structure of interest in metallic structures is called hexagonal closed packed, and an HCP. You can consider the packing of atoms in 3 different consecutive layers, A, B, C. So we have A and B and C layers. And C layer is identical to the A layer. So in essence, it's AB, AB, C, AB, AB kind of stacking. And what happens is that the A stacking, you get a hexagon, and the B stacking, you get another hexagon, but you get 3 atoms out of 6 sitting exactly in the center of the cube, so they will be sitting comfortably on top. This kind of crystal structure is associated with metals that are of interest to us, such as beryllium, titanium, hafnium, zirconium, cobalt, and so forth. So with these types of crystal structures, we will be using in design either face center cubic type materials or body center cubic type materials, and sometimes HCP type materials. Now I'm going to talk about defects. The crystal structure that you've seen is perfect. Every atom is occupying a site in space, and it has complete perfection when it is a single crystal. If for some reason one atom is removed, then the lattice site that has been left behind is now vacant, and that we call a vacancy. So this is a type of a defect in the material, and we're going to call this a point defect because it has very, very small dimensions, so we will borrow this word and label it as point defect. So this is a point defect, which is approximately considered to be 0D, 0 dimensions. And then we can also have a row of atoms that is missing, or rows that are inserted, and this can create a line defect, and therefore we give it the designation 1D, one-dimensional. We can also have one grain in a certain orientation, another grain in another orientation, and they're not fitting together. There is going to be an interface, and the interface is the grain boundary. And the grain boundary is considered a surface defect, and we will give it the designation 2D. And finally, we might have certain types of structures that do not belong in the lattice, for example, a void or a bubble, and that's a volume defect. So we're going to give it the designation 3D. So we'll just look at first point defects and move on to the other types of topological structures. So the point defect is an atomic size defect, and it can be either a vacancy or it can be an interstitial as well. So we might have a vacancy or we might have an interstitial. And the vacancy is, we talked about this, and the vacancy is one missing atom, such as this one, and we have a missing atom, and we have a missing atom here. So these are examples of vacancies. All of these are examples of vacancies. Another possibility is that if an atom is inserted where it doesn't belong, then we would have what's called as interstitial. And interstitial could be of a self type. The same type of atom of the surrounding lattice is just dislodged and moves to another position that is not equilibrium. Or it could, that we would call this intrinsic interstitial, intrinsic defect. Or it could come from outside. For example, if we have steel and then we put carbon atoms in, then the carbon is foreign to the steel, and it will be an extrinsic defect, point defect, that is introduced. So in phase center cubic metals, for example, we have either we have interstitial here in the corner, and surrounding this interstitial, you see that you have the nearest neighbors to this corner interstitials are 4 nearest neighbors, and therefore we're going to call this tetrahedral interstitial. If an interstitial atom ends up exactly in the middle, on the middle plane, then the nearest neighbors to it are actually the faces, the atoms and the faces of the cube, and therefore we have 8 of them, and therefore it is sitting in an octahedron that's surrounding it. So it's either that we have a tetrahedron, tetrahedral site, or an octahedral site that can accommodate an interstitial, whether it is self or foreign, that doesn't matter. The next type of topological defect is called a dislocation, and it's a line type defect. And prior to discovery of dislocations in crystals, around 1907, Volterra, who was a mathematician, have discovered or proposed that materials can deform in the following fashion. If you take a cylinder, and the cylinder as shown here in A, and then you cut it along this red line that I made, and you shift the cut by a displacement. This displacement, we call it the Burger's vector, and then you glue again. Then the surrounding medium, if this is a part of a surrounding medium, then the surrounding medium has an internal stress state that is locked in, and therefore you have a situation that has a stress inside, similar to what happens that can generate earthquakes, for example. So it's an internal stress state without external forces on the body. Now the shift can be either along this direction or along this direction here, or it can be also along this direction. So there's 3 possible orientations or directions for the shift before we glue. So after we cut, we shift and glue. So the orientations that I indicated here can give a situation in which we may have either a screw type dislocation, which is this configuration, or an edge type dislocation, and the edge type dislocation are one of these two configurations. They are both edge type dislocations. And in reality, in real crystals, you have dislocation loops that go from edge to screw, and therefore you can have mixed type dislocations as well. So if you look at the operation that we did on the past slide, then the shift is a vector, and it can have three different possible directions, and we're going to call it B from that point on. So it's a vector B, and that vector is called the Burger's vector. What I talked about is in any solid that doesn't have a crystal structure. If the solid now has a crystal structure, then these operations must be performed on a crystal lattice. So we have a process by which we can define the vector that delineate the shift, that is the Burger's vector, and we can define the direction that is tangent to the line defect, and that tangent we're going to call it the sense vector. So we have a sense vector, and this sense vector is tangent, zeta tangent to the line defect, and then the Burger's vector is the orientation of the shift. So for a crystal lattice, what we do is we make what's called a Burger's circuit. And the Burger's circuit, you have to have two configurations. One that is perfect, which is this configuration on the left. This is a perfect configuration. And one that is that contains the line defect, which is a configuration on the right. And then between these two configurations, you're going to do an operation by which you have a start point and a finish point. If you have a perfect lattice and you have a start point, for example, and this is your start point S in here, then you take a circuit, you take the same number of steps upward, 1, 2, 3, 4 steps upward, and then you take 1, 2, 3, 4 steps to the right, and then 4 steps down, and then 4 steps to the left. Then your finish point, if it is perfect, will coincide on the start point. So in that case, you define a loop in the material that is continuous loop, doesn't have any break in it. Now we're going to take, if we have a line defect, we're going to take a start point and a finish point and move the same number of steps, in elementary steps. So if we have the start point here, then we move 1, 2, 3, 4 here, and move 1, 2, 3, 4, and then we move 1, 2, 3, 4, and then we move 1, 2, 3, and 4. So when we have 4, then we ended up at point F, which is not the same as point S. Now the vector that connects S to F from start to finish is the Burger's vector. So this is the way we define the Burger's vector. And since the Burger's vector is perpendicular to the tangent line, zeta, then we have the condition, simple mathematical condition, that the dot product of B and zeta must be equal to 0 if it is an edge dislocation, and the cross product of B and zeta must be equal to 0 if it is a screw type dislocation. Next, I want to talk a little bit about dislocation mobility. How do dislocations move? We now understood that the motion of dislocations result in gross plastic deformation, because when you have a slip, it's not reversible. Dislocations, once they move, then it takes more energy to bring them back to where they started. And they can move by two processes. For example, if you look at the left here, you have a an edge dislocation, and the edge dislocation, if this edge dislocation moves on its glide plane, it produces slip. So it's like shift of atomic planes. If the edge dislocation absorbs vacancies, then it will move up, because once it absorbs vacancies, then the atoms are removed, and then the row of atoms that delineates the bottom end of the dislocation is not existent anymore, and therefore the dislocation line shifts up. On the right hand side here, you see a screw dislocation, and the screw dislocation can move either on a glide plane, or it can actually cross slip and move on another glide plane. In other words, the screw dislocation is not necessarily confined to move on its glide plane, and it can therefore move on any conjugate or similar plane in the material. And if it meets an obstacle like a precipitate, it avoids this obstacle by crossing over to another region in the crystal and continuing to move. So the screw dislocations are very slippery, and they can move around easily. The way that the dislocations exist, once we apply stress, the lines deform and they expand the area of slip. So if you look at the process shown here, it's called the Frank-Reed mechanism that leads to increase in the slipped area. So if you have a line, dislocation line here, and the dislocation line undergoes a force, a configuration of force, then the line expands, and as it expands, then it will continue expansion, it will wrap around itself, and then it will get to annihilate at some point, and therefore you're left with a loop on the outside that is expanding outward, increasing the slipped area, and the process has regenerated itself because you're left with the original segment that produces the loop in the first place. So this is called the Frank-Reed mechanism for production of dislocations, which we can see in action once we understand the process. So I'm going to show you now a little movie that illustrates the activities, dislocation activities. And this movie was made by simulations in our group, and the simulations actually simulate the motion of dislocations in materials. And I have also included a little bit of music in it, so you can see how actually the dislocation processes are simulated in materials. So what you see here are just basically dislocations of various colors, and the colors are actually, the colors indicate the dislocation slip plane. And here you can see mechanisms where you have cross slip of the dislocations forming a dislocation loop, and they call it dipolar loop. You can see now it's struggling, cross slip, and the dipolar loop formed and continues on. And as I mentioned, cross slip by screw dislocations is a very common process in materials and produces many of these dipolar loops that you will see in this movie. You also see other mechanisms. For example, here the multiplication by Frank-Reed sources that I indicated. You have many dislocations interacting and going to the boundaries of of the material and interacting with the boundary of the material. Here you will see that some dislocation patterns will form in the material, as a result of interactions. So it's like avalanches that are forming in the material, and dislocations move on different glide planes. That's why they have a variety of colors coming from the simulations indicating the formation of a pileup. We have a pileup here in the bottom, like in the, and so on. So now you get an idea about the process of dislocation mechanisms in here. So I'm going to just stop this movie here and then continue on in our discussions. So once we have the process of these dislocation mechanisms, we should be able to continue to look at surface defects. Surface defect is a plane that delineates two perfect crystals or crystals that have some imperfections. And the surface defects are classified as grain boundaries. They could be twin boundaries where one crystal is mirroring the other crystal, as I'll show you in a few minutes. Subgrain boundaries, and a subgrain is very similar to a grain boundary, except on a much smaller scale and less defined characteristics of the atomic planes. And then you could have also stacking faults within the crystal, so the atoms are not arranged exactly in their perfect lattice sites, but they can be shifted slightly to cause a fault in the stacking. And also you can have cracks in the material. Let's look at cracks, and cracks are classified as either mode 1, mode 2, or mode 3. So the mode depends basically on the way that the material opens up. So if the material opens up in perpendicular to the crack surface, that is called mode 1 or tensile mode. If the material opens up on the glide plane, either in the same direction of the applied shear stress or perpendicular to the applied shear stress, then we have mode 2 or mode 3. So mode 2, which is right here, is called the tearing mode, and mode 3, because it's twisting, is called the twisting mode of fracture. So now the next type of defect is a volume defect, and volume defects exist in the material in the form of voids, bubbles, precipitates, or even clusters of point defects or loops, similar to what you've seen in the dislocation movie, where you have these prismatic dislocation loops forming as clusters. So the growth of such defects can lead to premature fracture. And in fact, if you have voids on grain boundaries, they grow preferentially on these grain boundaries at high temperature. And as they coalesce on the grain boundaries will separate, and you get creep rupture. That is a very slow process where diffusion plays an important role until you get creep rupture. You can also, if you have gases such as methane or helium, when the gas is introduced in the material, the gas will find its way to these grain boundary bubbles, and it will make them expand even faster, and you get earlier failure of the material when you have gases inside. Now I'm going to spend a little time on the relationship between defects and the strength of the material. What is the role of the defect in the strength of materials? Well, we're going to assert that the defects result in a significant reduction in the strength of the materials. Could be many orders of magnitude. And therefore, we need to understand how do they affect the theoretical strength of the material. if we were to make materials without any defects, they will be incredibly strong. And let's try to examine this question here. To get at it, we're going to look at a bonding model between atoms, and the simplest bonding model is called the Lennard-Jones potential or the Condon-Morse interatomic potential. And in this bonding model, I have here V is the energy between two atoms in the material. We call it the potential, interatomic potential, the potential energy. And it's written as two terms. One term is repulsive, and the other term is attractive. So one push and one pull. So if two atoms come close to each other, the repulsive term B over R to the power M will be strong. If they try to expand away from each other, then the attractive term will dominate. So if you look at this kind of construction and you plot V as a function of the interatomic separation between atoms. So if I have an atom here and I have another atom here, and then I say that this distance between them is R. This is the distance between the two atoms. And then I plot the interatomic potential. You plot the previous equation, then you get a curve that looks like this. So this is, of course, it goes to 0 at infinity here. So the curve has, if you go too far, if R is very large, then they will pull at each other. If R is very small, then they will try to penetrate each other and therefore become repulsive, very strong repulsion. And there is going to be an equilibrium point in here, and the equilibrium point gives us this figure, is called R sub 0, which is the equilibrium distance between two atoms in the crystal. If we have a crystal, hypothetical crystal, based on the Lennard-Jones potential or the Condon-Morse potential, then R sub 0 would be called the lattice constant of that crystal. It's something on the order of 3.5 angstrom or so. Now, if I take the derivative of the potential, and the derivative of the potential is F is equal to minus dV by dr. So if I take this derivative and I plot the derivative as a function of R again, this is the plot of the force between atoms as a function of the distance, then you see that the force is 0 at the equilibrium point because the derivative of a minimum is 0. And then the force can be approximated as linear near that point. So a lot of times when you push atoms close to each other, we can approximate their behavior as linear elastic when they are pushed too hard against each other. So next is what type of information is needed to determine the constants that you see in this type of equation that is Lennard-Jones or Condon-Morse. Well, as you can see, you have 4 types of constants. A and B give you some kind of relative strength of the potential components, and then we have N and M, which gives you kind of indication on how fast the potential decays. One of the types of potentials used or was used in the past is the 612 potential, they call 612 potential. And the 612 potential is when you have the constant n in the exponent here as equal to 6 and the constant m as equal to 12. And in this case, the 612 potential, we can relate the lattice constant R0 to the ratio of the two strength constants A and B in the following fashion. If F is equal to 0 at R0, then we just substitute in the previous equation with n equals 6. So we have 6a divided by r to the power 7, and they have a minus sign, plus we have m now is 12b divided by r to the power 13, that equals to 0. And r in this case is actually r0 because it is the equilibrium constant that we're considering in this case. So we have the equilibrium constant in here, and we will use it in the calculations to determine the ratio between A and B. So having said that, you can solve this equation here, and you get the result, the following result. You get R0 raised to n minus m, b minus 6, equals to n times a, which is 6a, divided by m times b, which is 12b. And this solution here gives you a relationship that can be used to relate a measured quantity, and in this case, this measured quantity is the R0. We can relate R0 to the A and B, which are the constants used in the interatomic potential. So that's kind of an application of how we can compute the parameters used in the interatomic potential from basic material data. To get, for example, the B by itself or the A by itself, we need other properties such as the bulk modulus, and then we have to write an expression that relates the bulk modulus to the values of A and B, and therefore we have resolved all of the 4 parameters used in the interatomic potential. Now we're going to turn our attention to the question of why we cannot obtain the theoretical strength of the material. So to get to that question, we will look first at what happens when we get a row of atoms that is being dragged on top of another row of atoms. So for example, if I have atoms like this arranged in a stacking sequence like this, and then I have another red row underneath, so I have another row. Of course, each row represents a whole sheet of atoms going into the screen, and then I'm applying a shear stress in this direction, and then I'm looking at the centers of these atoms. How do they move? So we'll see if I plot now the centers of these atoms, then I'm going to select these 2 centers and then look at how the centers will move, and plot the potential energy as the centers move. And as you can see, that one atom is going to have to ride on top of the other one and fall down. So it goes up and down like this, and then it will continue in a fashion that looks like a sine wave. So if you plot the positions of these atoms, and in the notes it's plotted a lot better, but if we plot the positions here, then you see that it goes from equilibrium position, this is equilibrium here, to a maximum, and then it goes again to equilibrium. So you will have the potential V of R is going to look like a sine wave going from one equilibrium to another equilibrium, and it will have to go on top of the hill, which is this point here, to clear and fall down by itself. So if you take the derivative of this potential, you'll get a sine wave, which is what you have on the left. So the force is the derivative of the negative derivative of the potential. So the force here divided by per unit area is the shear stress on the material. So theoretically, the shear stress to move a layer of atoms on top of another layer can be approximated as in this fashion. We can approximate it as tau theoretical, which is the amplitude, the maximum amplitude, times sine 2 pi x over r0. And r0 is the center to center distance between the equilibrium positions. So this is r0. And on the left here, you see the way that we plot the shear stress of the material, the shear strength of the material as a sine wave. It depends on the position of the atoms as they move. So if we look at it a little bit closer, you see that this is the bottom layer of the atoms here, and the bottom layer is right here, and then the top layer is moving, and it moves from one position to another. But as it is displacing, and if the displacement is not too large, then we can approximate the displacement instead of, or the stress, instead of being a sine curve, we can approximate it as a linear curve. We can approximate the sine as a straight line. So we're going to use this idea. We know that sine x, for example, here, sine x is approximately equal to x when x is very small. So if we use this to approximate the prescribed shear stress function, then we get tau is approximately equal to tau theoretical times 2 pi x over r0, where r0 is the center-to-center difference between the atoms. On the other hand, this shear stress is a result of moving the whole entire crystal or trying to shear it. And from elasticity, if we consider the initial stage of motion as elastic, then from elasticity, this tau should be equal to the elastic modulus, in this case is the shear modulus of the material, times the ratio of the distance that moved, delta, this distance delta, divided by this height d. So this delta over d, that's the shear strain. So in our case, this delta is the same as x, just symbolically, and d is the same as r0, approximately as r0, because the distance between planes could be slightly different from the center to center distance between atoms, but we will take it to be equal to r0. With these substitutions, we can show that we have now on the left hand side is tau theoretical times 2 pi x over r0, and from the assumption of the dependence of the shear stress on the displacement of atoms. And on the right hand side is from elasticity, saying that the shear stress is equal to the shear modulus times the shear strain. And equating and utilizing the fact that d is approximately r0, then and then approximating pi equals 3 or 2.5, then you get tau theoretical is on the order of the shear strength of the material divided by 5. Now if I look at copper, for example, then mu is equal to 40 gigapascal. Then the theoretical shear strength of copper should be on the order of maybe 8 or 9 GPa. And that is extremely high strength of copper. In practice, copper, the yield strength of the copper yield point could be as low as maybe 20 to 40 megapascal. So we have a factor of almost 1,000 or 500 that is unaccounted for, and it makes you wonder why there's such a large difference between the observed and the theoretical shear strength of the material. So that kind of led to the idea that even if you use more accurate potentials and do these calculations much more accurately, then the theoretical strength is no bigger or smaller than, bigger than rather, mu over 30. So it's still very high. However, experimentally, we find that the theoretical shear strength of materials, metals in particular, is on the order of 10 to the minus 4 mu. And that is the difference that I was talking about, that between these two there's a big gap that can be only explained if we invoke the idea of crystal dislocations. And that's the idea that can lead to plastic deformation. So finally, I wanted to show here that the plastic deformation has 3 different modes, either slip, twinning, grain boundary sliding, or diffusional creep. Then the last 2, which is grain boundary sliding and diffusional creep, are important only for high temperature creep processes. So this is at T temperatures greater than half of the melting point. The slip and twinning are observed at lower temperatures and higher strain rates. So epsilon dot is high. The higher the strain rate, the more twinning we expect in materials or in metals. First, let's look at slip process. And the slip process here, I will explain it using a cylinder. And the cylinder here has a cross-sectional area A, and it has an applied force F on that cylinder. And on this cylinder, we have one plane, and this plane is inclined to the loading axis. So the loading axis is right there. This is the loading axis of the cylinder. So this plane here is where the shear process is going to take place. That is the most prevalent shear plane in the material where slip will take place by motion of dislocations. So in order for us to characterize the relationship between the slip plane and the normal to the loading or the loading axis, we introduce 2 angles. We introduce 2 angles. First angle, in order for us to define it, we will have to define the normal vector to the plane. So this is n, the normal vector to the plane. And we have also a vector here that defines the loading axis. Let's call it lowercase l. So this is lowercase l is a unit vector along the load. Lowercase n is a unit vector that is normal to the slip plane. And then there's also a third vector here. We're going to call it lowercase s. And lowercase s is a vector that lies on the slip plane, and it's a unit vector and defines the direction of slip. So I have 3 vectors, L and N and S. The dot product of L and S is defined by this angle lambda, so this is cosine lambda, and the dot product of L and N is defined by another angle called psi, and then we have this cosine psi. So these two will be useful in characterizing the slip mechanism in crystals. So if we study the resolved, first we want to have the resolved shear stress, then the resolved shear stress we have a force, and the force we divide it by the load, the area A, that's going to be the stress, the force per unit area that is on the area A. But that is not really what we consider important force for slip, so I need to get the force component on the slip plane. So instead of writing F over A, then we want to get the shear force on the shear plane, and this is, I have to project F on the shear plane, so I have the projection is F cosine lambda. So this is the force that is acting on the shear plane. And now I need to, in order for me to find the resolved shear stress, tau resolved, then I need to divide this force by the area of the plane. And the area of the plane now is not exactly A, but is inclined to A, with larger than A. So the area here, this is A prime, is equal to A divided by cosine of this second angle psi. So we have here A divided by cosine psi, and therefore I have now the resolved shear stress. I can write it in a fashion that is useful for me. So here is a recap of these relationships. I have the slip area is right here, and then the force on the slip plane, and then the resolved shear stress now is F over A times cosine lambda times cosine psi. And the criterion that we use for slip is called Schmidt's law. So Schmidt's law is that this resolved shear stress, if it exceeds a critical value that is measured experimentally, then slip will take place in the material and we get plastic flow. So to express Schmidt's law, then we say tau, let me write it down here. Schmidt's law is that Schmidt we have tau resolve must be greater than tau critical resolved shear stress, CRSS, critical resolved shear stress. So it's a number that is a function of temperature. On the other hand, we have another law that's called Zonke's law, which would govern whether a crystal will cleave or fracture by cleavage or not. And if we go through a similar analysis, we find that the normal stress to the cleavage plane, which is the same plane here, is equal to F over A cosine square psi. So the normal direction plays the main role, and we don't have to worry about the slip direction anymore. So Zonke's law again is that if sigma n is greater than sigma critical, then we would have a fracture taking place in the material. So we have sometimes to determine whether we would have fracture or we would have slip dependent on the value of the critical resolved shear stress versus the critical cleavage stress of the crystal. The critical resolved shear stress is obviously a function of temperature. And we would like to see kind of a plot that shows the temperature dependence of tau critical resolved shear stress versus temperature, and we kind of predict that the material is going to get softer at high temperature, and therefore the critical resolved shear stress should in general be a decreasing function of the temperature. And indeed this is the case, and we have now to look at the exact way that things look. You see here on the left side we get, for body center cubic materials like iron, the critical resolved shear stress is quite high because it takes a lot of energy to make these rows of atoms that I'm talking about to climb up and down in body center cubic materials. In the case of face center cubic materials, however, it doesn't take as much energy to climb up and down, and therefore the critical resolved shear stress is low, and these units are in PSI. So you have a few hundred PSI at the most, or maybe less than that for most face center cubic metals, while in body center cubic metals we require more than 10,000 PSI, and even at lower temperatures it will be much, much higher than this figure to cause slip by the Schmidt mechanism. In single crystal deformation, if we plot the type, or if we look at the mechanism of slip as a function of the amount of deformation, or as a function of the strain, we would discover that a slip, which is shown schematically here for a slipped crystal, is the process by which the planes kind of move relative to one another. We will discover that we have three different mechanisms. One is a linear or easy glide is called, and then as the strain increases we get into linear hardening, and then finally we get into a regime that is called dynamic recovery. And those regimes, they look at like this. So if you have now, if you plot the critical resolved shear stress versus resolved shear strain, then below 10% in copper you get easy glide, between 20 and 50% you get linear hardening, and above that number, above 40% straining, you get dynamic recovery and the formation of a substructure in copper. In the case of body center cubic metals, the situation is somewhat different, and we don't have these three stages of slip. We have linear increase in the value of the resolved shear stress with straining, and then it gets immediately into what is called parabolic strain hardening regime, where the material hardens and it looks like a parabola in this range here, and that's why they call it a parabolic strain hardening regime. The next topic is twinning, and twinning of crystals is very interesting, because in the twinning situation you get one part of the crystal becomes the mirror image of the other part of the crystal, and I have here the other part of the crystal actually is the blue part here. So the green top part is the mirror image of the blue part, and the blue part is another mirror image of the green part on the bottom. So we get basically two twin planes, and the crystal is mirrored across each one of these twin planes. So the lines that you see here are actually rows of atoms, and the rows of atoms, they get in one part of the crystal, they get at a different angle, and then they return to the same kind of orientation in the remainder of the crystal. And this kind of twinning mechanism is like a little buckling process that takes place inside the material and causes large strain stored in the material, but it could be recoverable, and in this case we call the behavior hyperelastic, and that's in shape memory alloys, for example, or it could be irreversible, and that is the case for twinning plasticity. So we have plasticity where the twin migration is locked, and we have irreversible process for the twin migration. Next process is at high temperature, and is only important to look at when you have creep conditions. And at high temperature, where we have the temperatures is higher than half of the melting point, then the application of stress, even small amounts of stress, will result in permanent deformation as a result of diffusion of atoms from one region of the crystal to another region. And generally, the grain boundaries are kind of good places to absorb the migration of excess atoms, or in this case, vacancies. So the grain boundaries themselves start to move, effectively move. And we would call this, you have effective viscosities, like you have two grains like this and they're stuck together, but they're sliding on one another, and the material can deform with this effective viscosity at high temperature. And I think this will round up all of the different plasticity mechanisms, and we have a good idea about the relationship between the defects and the strength of the materials. And we'll see you in the next lecture.